Okay, so this is my favorite chapter that we're starting, and we're starting in 6.1, verifying trig identities. So an identity is an equation that is true for all values of the variable for which the expressions in the equation are defined. So the left-hand side equals the right-hand side for any value of the variable. In an equation that is true for only some values of the variable, it's called a conditional equation. We're not going to be dealing with conditional equations too much or at all, and we're just going to be dealing with identities. So the first few identities, you guys already know. The reciprocal identities we've already derived, right? Cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tan. And you guys also know the quotient identities already. Tangent is sine over cosine, cotangent is cosine over sine. These are the new identities, the Pythagorean identities, but they're very easy to derive. So you can memorize them. Really, you just need to memorize the first one or know that quickly, and then the other ones are super easy to derive. So to start deriving sine squared plus cosine squared equals to 1, let's think back to our unit circle. I'll do my very best to try and draw a circle. Okay, so this is a unit circle, meaning this point will be 1, 0, this point will be 0, 1, negative 1, 0, and 0, negative 1. So let's think about having an angle theta that's in standard position, and this point where theta's terminating side passes through the unit circle would be cosine theta sine theta. And from here, if we thought about dropping a perpendicular so that we had a right triangle, we know the hypotenuse of that right triangle would be 1 because this is in the unit circle. This side of the triangle, this leg of the triangle, would be cosine theta, and this leg of the triangle would be sine theta. And we know that the relationship between the legs of a right triangle and its hypotenuse is the Pythagorean theorem, right? A squared plus b squared equals c squared. Well, if we just replace a and b with cosine and sine, and then c with 1, we end up with our first Pythagorean identity. Sine squared plus cosine squared equals to 1. Now, the other two identities we can easily derive from this first identity. If we were to think about dividing each side of this first identity by cosine squared, and I guess before I go any further, I'd just like to note that when you guys see like cosine with this 2 here, that's cosine squared. That's equal to cosine times cosine. Okay, so that's the exponent. We don't have it on the x or on the outside because we're lazy. We don't want to write the parentheses and then raise to the exponent of 2. And then we don't want it to look like the 2 is on the x. Okay, so going back to deriving our next identity, if I've divided each side of this first identity by cosine squared, notice that sine squared over cosine squared is equal to tan squared. Cosine squared over cosine squared is just 1. And 1 over cosine squared is actually secant squared. Since 1 over cosine is secant, 1 over cosine squared would then be secant squared. And then to backtrack, to derive the last identity, so to derive 1 plus cotangent There should be an x there. Cotangent squared equal to cosecant squared. We would want to divide each side of the first identity by sine squared. So then we would end up with sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. Since cosine over sine is cotangent, then cosine squared over sine squared is cotangent squared. And 1 over sine squared is equal to cosecant squared. So you're easily able to derive all three of those identities. And the even odd identities we have already derived. You guys know these. And you should know what each of these sets of identities are called. Like you should know these are the quotient identities, these are the reciprocal identities, Pythagorean identities, even odd identities. So we're going to start with simplifying trig expressions using identities. So basically we're going to take complicated trig expressions and try and use our identities to simplify them. Okay, make them less complex. So our strategy, or one strategy you could use for simplifying trig expressions, is to first rewrite everything in terms of sine and cosine, since all of the other trig functions can be written in terms of sine and cosine, or ratios of sine and cosine. So with this first one, we're going to rewrite cotangent as cosine over sine and then if we rewrite that, that's cosine squared over sine. Okay, and if we want to simplify this more and make this into one fraction, we can multiply here by sine over sine, so multiply by a version of 1, so that we have cosine squared plus sine squared over our common denominator of sine. And then we see that cosine squared plus sine squared is actually just 1. So we have 1 over sine, which is just cosecant. So that complicated trig expression is actually just equal to cosecant. Okay, if we look at this one, we could rewrite 1 over cosine squared as secant squared. And then if we think about our Pythagorean identities, we go, oh, okay, well, we know secant squared and 1 are both part of a trig identity, the Pythagorean identities, right? So if we go back up here, if we were to subtract 1 from each side of this identity, we would see that secant squared minus 1 is actually equal to tan squared. Or you could recognize that you could just replace secant squared with tan squared plus 1, which is the trig identity, right? Tan squared plus 1 equals to secant squared. And then we already have the minus 1 from above. So this is just equal to tan squared. And there's a couple different ways you can look at simplifying that. So now we're going to hop into verifying identities. So verifying identities is fun. You want to think of it like you're solving a puzzle, or that's the way I like to think of it, where you're given an equation. Like you're given that the left-hand side is equal to the right-hand side, and you are proving, it is your job to prove that the left-hand side equals the right-hand side. So you're going to I have some tips and tricks here. So my suggestion is to look at the identity, look at the equation you're given, and choose the more complicated side to try and work on. And then you can combine all sums and differences of fractions into single fractions. And then, like before, it's helpful to convert everything into sines and cosines if you don't see anything else you can do. And then just use those fundamental trig identities. All of these identities that we're going to verify now are going to be using the identities that we have above. So the Pythagorean ones, remember, are the only new ones to this lesson. Now, super important, you cannot use any properties of equality. There's no adding a value to each side. There's no subtracting, no multiplying, no dividing. You are only to work on one side of the equation. If you get stuck, you are welcome to start over and work on the other side of the equation, but you may not use any properties of equality. Okay, so looking at this first identity, switch colors. So looking at this first identity, the left side obviously looks a lot more complicated. So let's start by changing the left-hand side to be in terms of sine and cosine. So tan we know is sine over cosine. Cotangent is cosine over sine. Okay, so we're going to work down the left-hand side. I'm going to move this over just a little bit so I have a little more room. To get rid of the complex fractions, I'm going to multiply by cosine times sine over cosine times sine, right? You can multiply by 1. It doesn't change the value. So if we think about distributing cosine times sine to this first fraction, notice that the cosines will cancel and we'll be left with sine squared. And then if we distribute to this next fraction, the sines will cancel and we'll be left with minus cosine squared, which is looking good, right, for what the right-hand side of the equality looks like. Then in the bottom, or in the denominator, we distribute cosine times sine. Notice cosines will cancel again, so we'll be left with sine squared. And distributing to the last fraction in the denominator, sines will cancel and we'll be left with plus cosine squared. Okay, almost there. We notice this one, I love when this happens. When we get sine squared plus cosine squared is actually just 1. So this is actually just equal to sine squared minus cosine squared. Done. Okay. Now, left-hand side to me looks more complicated. Remember, you can work the left or the right-hand side. The other thing that's important to remember that is if you're checking work with your friends, their work might look different than yours. The steps that they took, the identities that they chose to use might be different than yours. And that's okay. That's kind of the cool thing about these. So I'm going to work on the left-hand side. So I'm going to try and rewrite the left-hand side as a single fraction, which means I'm going to multiply the first fraction by 1 minus sine over 1 minus sine. And I'm going to multiply the second fraction by cosine over cosine so that we can get a common denominator. Okay, so that'll give us in the numerator 1 minus sine squared, the quantity 1 minus sine squared, plus cosine squared. over 1 minus sine times cosine. We get kind of stuck here, so the only thing that I see we can do is to multiply out and combine like terms in the numerator. Please remember that's not 1 minus sine squared. That's the quantity 1 minus sine times the quantity 1 minus sine. So when we expand, we get 1 minus 2 sine plus sine squared plus cosine squared all over 1 minus sine times cosine. Yay! That's just 1. So in combining like terms, we'll get 2 is equal, sorry, not 2 is equal, 2 minus 2 sine of x all over 1 minus sine times cosine. And if we look at the right-hand side up here, we notice there's a 2 there, so we're on the right track. We can factor a 2 out of the numerator. Which will allow us to cancel 1 minus sine over 1 minus sine. And I've run out of room, but we're going to be left with 1 over cosine, sorry, 2 over cosine, which is 2 times secant, right? Because 1 over cosine is secant. So, done. I should have added another page. Sorry about that. Okay. So for this next identity, what sticks out to me is the negative 1 being multiplied by the argument here. So we can use our even-odd identities. Sine is odd, so the numerator can be rewritten as sine, negative sine of x, over cosine is even, so cosine of x, and then tangent is odd, so I'm going to pull that negative out front to rewrite the denominator as negative cosine times tangent. And then those negatives will be able to cancel. So we just have sine over cosine times tan. Now you have options here. You can either notice that sine over cosine is actually going to be tangent, or you can change tangent to be in terms of sine and cosine. So if you recognize that sine over cosine is actually tangent, then you just end up with tangent over tangent is equal to 1. Or if we change tangent to be in terms of sine and cosine, so sine over cosine is tangent. Notice that the cosines would cancel, so we would be left with sine over sine, which is just 1. This is our last one. Okay, so trying to decide right or left. Both look pretty complicated. I'm going to use the right-hand side since the left-hand side is already in terms of sine. Now, negative cotangent squared. We do have the option of changing everything to be in terms of sine and cosine. But I like to use those Pythagorean identities. So remember that 1 plus cotangent squared is equal to cosecant squared. Okay, so if we were to subtract cosecant from each side and subtract cotangent squared from each side, we would get 1 minus cosecant squared is equal to negative cotangent squared. So I'm going to replace negative cotangent squared with 1 minus cosecant squared. Then if we recognize that the numerator is actually a difference of two squares that can factor, just like any difference of two squares, okay? Now we can see 1 minus cosecant will cancel 1 minus cosecant. And we're almost there. I'm going to add a page instead of writing on to the next one. So we know that cosecant can be written in terms of sine. So let's rewrite this as 1 plus 1 over sine. And if we rewrite 1 as sine over sine, then we just end up with sine plus 1 over sine. Done. This last, nope, not yet. Okay, left or right side? Hard to say. I would probably work on the left-hand side since it's a difference. And I always have the option of trying to combine into a single fraction, because 1 over cosecant I can write as 1 over, cosecant I can write as 1 over sine. Let's see. And then if I get a common denominator, I'll have 1 minus sine squared over sine. The numerator here is equal to cosine squared from the Pythagorean identity. If we were to break up cosine squared and think of it as cosine times cosine, then cosine over sine we know is cotangent. I have to be able to follow these steps, you guys. They have to make sense. It needs to be very obvious going from one step to the next. Because you're given that these are equalities. You're given the left-hand side equals the right-hand side, and you're proving it. Okay, last one. Okay, I'm thinking left-hand side. So I'm going to multiply the first fraction by 1 plus sine over 1 plus sine. And the second fraction by 1 minus sine over 1 minus sine. Okay, so our denominator is actually going to be a difference of two squares. So 1 minus sine squared, if we multiply that out. And in the numerator, if we distribute the cosine, we'll have 1 plus cosine times sine. Okay, that'll be minus cosine. And plus cosine times sine. Yeah. Okay, so that's going to give us, what am I missing? Oh, I forgot when I first distributed that that's cosine. Cosine times 1 is cosine. Okay, so the cosines are going to cancel. Here we go. I'll leave us with 2 cosine. Yeah. Now, we need 2 tan of x. We have the 2. Tangent is sine over cosine. So what if I rewrote the denominator as cosine squared from the Pythagorean identity? So then we could cancel a cosine from the denominator with a cosine in the numerator. And that'll leave us with 2 times sine, oops, wrong color. 2 times sine over cosine. And we know sine over cosine is tangent. Okay. Try not to get frustrated with these. Think of them as puzzles. Remember, you can work either side. And if all else fails, change everything to be in terms of sine and cosine. And we are going to tomorrow be adding some more identities to our toolbox.